Well, guys, okay, this is just to give you some brief explanation of why inflation is actually a natural generator of primordial fluctuations, because actually this is, in truth, why inflation is so relevant for us. Well, basics of inflation is that you start at some moment with, for instance, a slow roll picture with very small slow roll parameters until they become order 1. This takes of the order of 60 foldings, which is enough to make very flat the universe and solve the horizon problem. Is that all? No, that's the background picture. Of course, if you think of the inflaton as responsible for inflation, nothing is gonna prevent you from thinking that it has fluctuations. Simply because quantum mechanics exists, you know, and this field is gonna be, the fluctuations are gonna be in a low occupation number. And if I can think of fluctuations, nothing is going to prevent me from thinking of fluctuations of the metric as well. So essentially, why fluctuations? The answer is because quantum mechanics exists, is there, it's unavoidable as far as we know for fields. And therefore, I want to consider quantum mechanics applied to these fluctuations and to the metric fluctuations as well. So think of now promoting this to an operator. This means that there is an expectation value. This is the background value of the inflaton, but that doesn't change the fact that on top of that I can consider fluctuations, okay, quantum mechanical fluctuations. And the same goes for the metric. Now think that the expectation value of these fluctuations might be vanishing because I'm gonna fluctuate randomly if I repeat the experiments of measuring these fluctuations up and down, but there's gonna be a variance, which is going to tell me the typical amplitude of these fluctuations, right? So essentially, because now we are, remember, in a curved space-time, things are a bit complicated, and the degrees of freedom of matter are going to be related to the degrees of freedom of the metric. I do the standard decomposition, a scalar vector tensor, which you know very well by now, and as we discussed this morning, the decomposition is such that during inflation I don't care about vectors because they decay away, and we only focus on the scalars and pure tensors, which we identify with gravitational waves. We already learned this morning that the scalars, of course, are not gauge invariant, so you have to make combinations of them such that you can build then really gauge invariant quantities, and the tensors are gauge invariant directly. Okay. So imagine we fix the gauge in such a way that the only scalar we follow is this curvature perturbation R, and then we also keep the tensors. This is the exercise that people did in the early 80s to understand now fluctuations during inflation. So I have this. Well, I should have also here curly R, okay? So the full metric is this guy plus this guy, but I only have curly R and tensor Hij. I plug it into my full actions, Hilbert-Einstein term for gravity plus matter action. And if I do that, what I get, now expanding to second order, now we have practice in doing this, is this kind of actions. For the scalar fluctuation, we get some kind of what it looks harmonic oscillator type of thing times all this complicated variable. And for the tensor, we also get some kind of harmonic oscillator times this volume factor, deep inside the Hubble radius, okay? These expansions are done deep inside. Good. So, I mean, of course, doing this expansion is involved, as you learn, you know, on the second lecture, but let me use now this. So essentially, if you have this as a starting point, I can make a change of variables now, a clever change of variable. This is what Mukhanov actually did 40 years ago. He defined this new variable, which is proportional to curly R times this other guy, which was what I had here outside. So he reabsorbed that in the variable, and then he wrote the action for this new variable, which is the Mukhanov-Sasaki variable, V. And what this looks like is really a time-dependent harmonic oscillator, where the time dependence is in this term. So, yeah. Good. So if I write now the equation of motion of the mode functions of this new field, mode functions are just the Fourier transform modes, well, there should be there should be a proper quantization here, and I should have creation annihilation operators times the the mode functions, which are these. This is what the equation looks like now from this action. It's a harmonic-like oscillator, which is not really harmonic because I have a time-dependent frequency, and the time dependence comes literally from the fact that I'm in quasi-de Sitter, 1 over tau squared, times this prefactor, which depends on the slow roll parameters, which to first order they are constant. So essentially, in slow roll physics, when you do all this computation, what you get is that all the time dependence comes from 1 over conformal time squared times some constant that depends on the slow roll regime. Okay. Why are we doing this? Because this equation actually can be solved exactly, analytically. Actually, these were really my Fourier modes. Now I promote them, I quantize them, and I really promote them into this linear combination of mode functions and creation annihilation operators, which contain the quantization information. And essentially, there are going to be always two linearly independent solutions to this second order differential equation. And these are Hankel functions, but I can kill one of them and only retain this one, simply because this is the exact solution, and I want the exact solution to be such that deep inside Hubble, it reduces to what we call positive defined frequency. What is this? This is the standard vacuum in quantum mechanics that you are familiar with. If you don't know what I'm talking about, I refresh it to you. So essentially, when you have a harmonic quantum oscillator, and you ask you what is the quantum state of zero of the minimum energy, essentially what you get is this 1 over square root of 2 omega k, where omega k here is dominated by the frequency, by k, not by any mass. So essentially, I want my mode function to go deep inside the Hubble scale to this functional form. And I want to keep the positive frequency defined. Had I kept the other Hankel function, I would have obtained the opposite phase here. So I want to keep this so-called positive defined frequency, which has the minus here, because that's the one that if you take the Hamiltonian operating over this mode function, it will give you positive defined energy. Had I kept the other Hankel, then I would have kept the plus here, and that's called the negative defined frequency, because the Hamiltonian will give me the minus k energy. Okay, so we want, obviously, our mode function to have positive defined energy, and that's why we retain only one of the Hankel functions, and we have to make sure that this guy really flows into this solution deep inside the Hubble scale. Do you understand this? Or is this clear at all? So essentially, you know, I'm just solving this differential equation in the slow roll paradigm where this is a constant, and I can do it exactly. And the only physical constraint I can really impose in my system is that deep inside the Hubble radius, I want to recover a standard quantum mechanical vacuum for positive defined modes. And a standard quantum mechanical vacuum means that the typical amplitude is 1 over 2k, so that the expectation value of this is 1 over 2k without the square root. If you go to your quantum mechanics book for the quantum mechanics oscillator, harmonic oscillator, you will discover that. And that's all is happening here, because look at this look at this equation. Deep inside the Hubble radius, this k squared dominates over this guy. So I only care about k squared. Hence, my solution is going to be only positive and negative frequency modes. And as I insist on having only the positive frequency mode, I discard the other Hankel function. And I rearrange my perfactors here such that when I take the limit of sub-Hubble scales, I flow to this solution. Okay, that's all I'm doing. This is called the Vance-Davis vacuum. The Vance-Davis vacuum is nothing but the vacuum in quasi-de Sitter that mimics the standard quantum vacuum deep inside the Hubble radius, because deep inside the Hubble radius, I don't see the expansion of the universe. I'm only dominated by the k squared term. Yes? Good. So if I have this, it means I have the solution to my vacuum fluctuations in quasi-de Sitter, as long as they are deep inside the Hubble radius. So this is my initial condition. These are my quantum vacuum fluctuations when the modes are deep inside the Hubble radius. But because we are in inflation, the initially sub-Hubble wavelengths are gonna start approaching exponentially the Hubble radius. They are gonna exit the Hubble radius, remember. So essentially, I can take the expectation value of my quantized curvature perturbation, which I undo now in the form of V over set, and remember set is just this combination, and now I can predict what is my expectation value. My expectation value is based on taking this guy, you know, you are gonna rescue only Vk times Vk star, and this is gonna give you this. So it's the square of this guy, essentially the inverse of this guy, and the square of the mode function, the absolute value. So I am predicted what's the variance now of my quantum mechanical fluctuating perturbations. And this is what we call the scalar power spectrum. Now it turns out, well, I've changed notation, I don't know why, it's still conformal time. You can define, if you want, your dimensionless scalar spectrum by multiplying by k to the 3 the previous expression here. And the point is, because I do have the analytical expression of this guy is here, I can evaluate now this at super Hubble scales, the opposite regime, just because I know the wavelength is going to cross the Hubble radius and it's going to become super Hubble. If you do that, you take this expression of the Hankel and this guy here, the amplitude flows to this expression. Okay, that would be the exercise for you to do. It's not immediate, but it's all here, really, in the solution. Both limits on the UV, deep inside the Hubble radius, to Banks-Davis vacuum, or to the infrared when the mode leaves the Hubble radius, and it goes to this expression. And this is the famous expression that characterizes the amplitude of the variance of the quantum vacuum fluctuations, which now are not vacuum anymore, because essentially the occupation number, if I were to show it to you, which I don't have the transparency here, has grown exponentially. This is precisely what quantum mechanics, what de Sitter does to quantum mechanical initial fluctuations. Because of the exponential expansion, not only stretches exponentially the wavelengths, it also boosts the amplitude according to this evolution, and this corresponds to an excitation into a classical regime of the fluctuations. So now this is the expectation value of a stochastic but classical background field, not background, field, you know, of fluctuations. And this is the famous prediction of inflation of the power spectrum for scalar fluctuations with a tilt depending on the slow roll. And I can do pretty much the same with my tensor fluctuations. Essentially, I now decompose them into polarizations, and I write in a canonical normalized manner the graviton multiplying by the Planck mass here. So I write my action in terms of these V functions now, which again they have a time-dependent frequency. Pretty much the same procedure as before. You quantize your Fourier modes, then you impose Banks-Davis deep inside the UV, and this defines the power spectrum, and essentially it will flow in the infrared into this expression with your Hankel solutions, which now depends only on the Hubble rate square. So it's sensitive directly to the energy scale of inflation. Whereas before, look that it depends on the Hubble scale to the fourth, but also the kinetic energy of the inflaton. And due to this degeneracy, the scalar spectrum that has been measured with exquisite precision at the CMB scales, however, cannot tell you about the inflaton energy scale. If we were to detect these tensor modes with the CMB B modes, then we would have a proof of the Hubble rate at the moment of horizon exit of these guys, and hence of the energy scale of inflation. Okay. So that's the quantum mechanical origin. I don't know how clear or easy it is to you, but you have not the algebra, but the details there. And if this is not clear enough, I would strongly suggest, if you are interested, to look at the review of Daniel Baumann, where he derives in full detail this calculation. and hopefully there will become more easy to follow. Okay? Yeah, that's it. Any questions? Any criticism, you know? Who had ever seen this kind of calculation? Okay, so few people. Yeah. I see. Yeah. Well, I don't know, maybe I don't have my monkey to put it here, but guys, this is mind-blowing, you know? This is inflation telling us that just because there is quantum mechanics and we are inflating space, the initial quantum fluctuations that you normally wouldn't care about them because you would renormalize them out, you know? It's like what in standard quantum field theory with normal ordering, you kick out and you don't care. Here they come to life, just because they are being stretched due to the exponential expansion. And they become macroscopic, classical. And they actually are the origin of structure formation. Because without them, not only we cannot explain the CMB anisotropies, we certainly wouldn't have any initial seed to start structure formation. Okay. So that's why inflation is mind-blowing, because it really provides, in a very natural way, just advocating quantum mechanics and field theory, so quantum field theory, the origin of structure in the universe, or the origin of the primordial fluctuations, like this.